Hey, AB Calculus, it's Mr. Canfield. Today we're looking at the optimization problems, some of the coolest problems we get to do this part of the year, and nice and straightforward. So optimization, what does that word mean? Optimal, you might have heard that before. Optimal meaning best, right? So let's say that we're trying to build a shed, right? Stu gives us two good examples of this. The first one is you've bought a certain amount of materials, so use those materials to build the biggest shed that you possibly can. The shed with the biggest area, let's say. Kind of ignoring the actual volume of it and just thinking about the footprint of it. Another form of optimization problem that we get is instead decide the area that you want, and then you optimize the materials that you buy, so you purchase the least amount of materials to build that shed. So kind of two sides of the same coin. Yeah, those are some examples. So what we are going to do is there's a general method for doing this. Basically, first you read your problem and you figure out, is this actually an optimization question? So we're in the optimization section. Of course, all the questions are optimization problems. But on the AP exam, you're going to read it and you're not necessarily going to know. So we're going to look at some of the key words that define them, that help us decide that it's an optimization question. So that's the first thing. Second thing we're going to do is we're going to write down the equation that we're trying to optimize, and it might have a bunch of letters in it. Essentially, what we are trying to do is we're trying to get some kind of function to be in one variable. A lot of times we're going to wind up having a function that's in multiple variables, and it's not a function of a single variable, so I guess function's the wrong word. We're going to have an equation, and we want to convert it into some kind of function, because then we can take the derivative of it, and then we can find min or max, because hey, optimization is all about finding the minimum or the maximum. So this is just an applied relative max or min problem, essentially. Sometimes absolute max or min problem. Okay, let's jump into our first example. Number one at the bottom says two numbers sum to 40. I'm hiding it because I have my work from when I've done this in the past. Find the numbers that maximize their product. Okay. So let's look at the key words here. Complete the chart. No, I'm not going to. Two numbers sum to 40. Find the numbers that maximize their product. So what equation are we trying to optimize here? Well, we're trying to optimize product. It says we want the maximum product. So what I would write for number one is I would write product is equal to, and it says two numbers, right? And we get to choose whatever letters we want for these things. You could choose A times B, you could choose F times U. I'm gonna choose X times Y just because, you know, I'm used to doing that. Two numbers sum to 40. Okay, well that sounds like something else that's true. Well, what are my two numbers? My numbers are X and Y. So I'm able to say X plus Y is equal to 40. So I've got a system of equations here, and at the end of the day, we want to maximize product, right? That means that we want to take the derivative of product. We want to take the derivative of P, but we don't want to do it with two different letters. We just want to do it with a single letter. So what I'm going to do is I'm going to take this and substitute. So I'm going to solve this for, it doesn't matter. I'm going to solve this for X. So X is equal to 40 minus Y. Okay. So I'm going to say P is equal to 40 minus Y times Y. Before I take the derivative, I am going to distribute the Y. So I get 40Y minus Y squared. Okay. So now P is just a function of Y. So if I take the derivative, P prime is equal to 40 minus 2Y we have to go through the process of finding any relative extrema. And so there's a couple ways we can do that. I'm going to go through and do my favorite method. I'm going to, well, set it equal to 0. That's not an option. We've got to find the critical numbers first. All right. So you might already know what it is, but I'm going to add the 2y to both sides. Divide by 2. We get y is equal to 20. So I got to find out, though, is y being 20, is that a max or a min? So the way that I'm going to choose to do this is by finding the second derivative of p. This is a very quick way. So p double prime, at least for this problem, p double prime is negative 2. That means p double prime is always negative. And what does double prime tell us about the original? It tells us concavity. This means it's always concave down, which is this shape, right? So that means that this is at that point. So it's a max. Y is 20 is a max. Well, what's my other number then? Oh, I know x plus y is 40, so it's also 20. So it turns out that if two numbers add up to 40, the way to get the maximum product is to go dead set in the middle and do 20 times 20. It does not actually ask for what the product is, so we're done there. The product will be 400. And if you don't believe me, try any other numbers. But the product is a whole bunch of different things. We took the derivative. The product changes as y changes, right? It changes as x and y change together, but we know that we can convert it just to say we can look at it as y changes. So we're able to say that the product attains a maximum when the derivative is 0 because it's concave down. So this is all but proven. All right, let's see. You might be like, well, what about negative numbers? The problem is if I use something like -5, then I have to use positive, like if x was -5, then y would have to be positive 45. And when you multiply those, you get a negative number. So it turns out there is no actual minimum value because we could keep on, I could say -1,000 and then positive 1,040. That adds up to 40. And that's a huge negative number, but if we want a maximum product, we're looking at positive numbers there. Okay. Egg sample 2. I did say egg sample, not example. Wow, those sound the same coming out of my mouth right now. Guess my allergies are acting up a little bit. Okay. Oh, somebody already underlined this for me. Thanks, me. Find two positive numbers, a and b. Oh, this time they tell me the letters. That's, no, thanks, do. That minimizes the sum of twice a and b if the product of the two numbers is 288. Complete the chart. No, we're not going to complete the chart again. You're welcome to complete the chart, but I just want to focus on the calculus of it. It might be helpful. Feel free to do it. Okay. What are we trying to minimize? The sum of twice a and b. So minimize that. That is like our clue, right? Minimize the sum of twice a and b. Okay, so we've got to talk English. Minimize the sum. Well, the sum is a plus, right? So, and I can use, like, I want to say that whatever this thing, however I write this, that's equal to my sum. So, shoot. So I could write, whatever letter you want for sum, I'm going to write the letter S. Just try to make it not look like an 8. That looks like an 8 now. There. Now it maybe it looks more like a cursive S. So sum of twice A and B. So is this 2A plus B, or is this 2A plus B? So I would argue that this is twice A, 2A, and B, and not 2 times the quantity A plus B. I think that if it was going to be 2 times the quantity A plus B, come on, it's not that boring. No, I'm just tired. If it was going to be this, it would be twice the sum of A plus B, where twice affects what it's doing. And then it says the product of the two numbers is 288. That means that AB is equal to 288. Okay. So whatever our optimization equation is, our max equation or our min equation, that's the one we're going to take the derivative of. That's the one that I need to go in and get rid of one of the other letters, or essentially all of the other letters. It's just there's only one this time. And you get to pick. Do you want to get rid of A? Do you want to get rid of B? Well, here's the thing. If I am going to be dividing both sides by one of these letters over here, and then going back and substituting, it might be better. I was going to say it might be better to do this one because there's a 2 already there. I'm going to divide both sides by A this time because I can. So B is equal to 288 over A. So I can say sum is equal to 2A plus 288 over A. And you might be tempted to like do work here. Don't do work. Don't do work. Just take the derivative. S squared. Yeah, good job, Canfield. No, S prime is equal to 2. Now this right here, how do we take this derivative? Remember, this is 288 a to the negative 1, right? So that'd be negative 288 a to the negative 2. Or you could just say minus 288 over a squared. All right. So now I'm supposed to find critical numbers for this. I'm supposed to find any place where the derivative is 0 or undefined. Well, the derivative would be undefined when a is 0, but read the problem again. Find 2 positive numbers. 0 is not positive, so 0 doesn't matter. I just need to find out when the derivative equals 0 then. So running low on space. All right, so 0 is equal to 2 minus 288 over a squared. I'll add the 288 over a squared to both sides, and then I'm going to multiply both sides by a squared. So then a squared is equal to 144. Take the square root of both sides. You get a is equal to plus or minus 12. But if you remember this problem, it said we want positives, so a is 12. And that means that b, well, we know that a times b is equal to 288, so b is equal to 288 divided by 12. Oh, and we even said that b is equal to 288 over a. So 288 over 12, that, what is that, 24? It's one of those things where I'm like, I am like 99.9% sure I'm right on that, but I make enough silly mistakes, may as well check. So there we go. Oh, I forgot to check, is this a max or a min? Here's the thing. 9 times out of 9.5 times. This is almost every time. This is it. This is the answer. So these are your basic optimization questions. Now we start to get into more applied questions. Why did I write negative 36 there? I don't know. A rectangle has a perimeter of 71 feet. What's the maximum area of the rectangle? Okay, so once we get into anything drawable, I like to draw it to give myself like some grounding. So I'm gonna draw a rectangle, and I know the perimeter is 71. Maximum area. Oh, that's an optimization word, maximum area. So I'm gonna take my area. I know area is BH, or L times W. So this is my optimization equation. This is the one I'm going to take the derivative of. I need to get rid of one of these letters. I need it to just be a single letter. And again, it doesn't matter which letter. I know P is equal to 71. Maybe there's something I can do with that to get this. Well, you know, this is B, and this is B, and this is H, and this is H. I do know that perimeter 71 is equal to B plus H plus H. And if you're like, are you seriously writing it like that? Yeah, why not? So perimeter is equal to, wait, no. We know perimeter. Perimeter is 71. 71 is equal to 2B plus 2H. So we could say, if we want, that pick a letter, doesn't matter. I'm going to subtract 2H and then divide by 2, and that is equal to B, right? So I can go over here, I can say, hey, A, you're equal to 71 minus 2H over 2 times H. So let's make this look a little bit nicer. I can distribute the H, 71H minus 2H squared over 2. When I go to take the derivative of this, some of you are going to do the quotient rule. Quotient rule will work, but remember, this is over a constant. We could really think about this before we take the derivative. We could think about this as 71 over 2H minus 2 over 2H squared, or just H squared. That is not only allowed, but it is very true. I am going along with Stu's answer key today because I'm tired and I just don't want to make any silly mistakes. He uses 35.5 instead of 71 over 2. And that's where we can get snooty and like turn up our nose at it. I'm not going to write a decimal, I'm going to leave it as a fraction. And if you were like, Canfield, I wrote 35.5. No, that's awesome, that's great. All right, so we'll take the derivative, get 71 over 2 minus 2H, and we just want to find the critical points. Let's see, so set it equal to 0, 71 over 2 minus 2H, 2H is equal to 71 over 2, divide by 2, get H is equal to 71 over 4. All right, so that is our height. So then we want to find the base. The base is annoying, but okay. Because I know that 71 minus 2H over 2 is equal to my base. I'm going to commit. I'm going to keep on going. Keep on doing fractions. 71 over 4. Okay. So that's 71 over 2 minus the 2's cancel, 71 over 4. You see that I put them both over 2, so then it was 2 times 71 over 4 divided by 2. The 2's cancel. I got to make this have the same denominator, so that's times 2 times 2. So that's 142 minus 71 over 4. which is 71 over 4. Now, it says, what's the maximum area of the rectangle? Maximum area of the rectangle is gonna, wait, this isn't a rectangle. Well, it is a rectangle. Look at that, look at that. They're the same number. It turns out that in a lot of these kinds of questions, when it's a rectangle, when it's a box, when it's a tank, a lot of times symmetrical shapes and shapes that are equal in all directions, like cubes and spheres, and those wind up being optimal. In this case, a square is optimal. 71 over 4 squared is equal to our area. No, I don't care to find that number, but I know that it's not good enough for some of you. 315.0625 feet squared. That's our maximum area. Okay, so this problem is a contrived problem, and contrived means like made up for the sake of making it up, or like making it up to like for the sake of it. Yeah, I guess that's a good enough explanation. Because it says a rectangle has a perimeter of 71 feet. What's the maximum area of the rectangle? A way that you could immediately turn this into a more realistic problem is to say you have 71 feet of fence to use. You're gonna make a rectangular fence. What is the biggest area you can enclose with that fence? And all of a sudden, this exact problem becomes a very realistic problem. Okay, I can afford this much fence. How much of my backyard can I fence in? I can fence in 315 point that feet squared. And you know that turns out the way to break it up the best is make a square. So there's lots of options, and then we find the optimal option. All right, next problem. An open box is made from a piece of metal 16 by 30 inches by cutting out squares of equal sides from the corners and bending up the sides. What size square should be cut out to create a box of greatest volume? And what is the volume of the box? Complete the chart. Again, we're not gonna do the chart. Okay. You can read that a couple of times if you need to. I'm gonna show you on a piece of paper what this is talking about. This is a classic problem. Everybody who's gone through calculus has seen problems, has seen this problem. Maybe the numbers are a little bit different, but this idea. So, open box. What are we trying to optimize? We want greatest volume. Oh, wait, what is the maximum? Okay, so yeah, we want to maximize volume. Well, I know volume of a box, and since this is a three-dimensional shape, the volume would be given to you. But the volume of the box is given by length times width times height. Or I guess, would that be base height and depth? Whatever. LWH. I'm going to need to somehow take this and convert this into only a single letter. We'll get there, don't worry. So I'm gonna show you on paper, or sorry, like with a physical model, what this is, but then we'll look at how to do that. So let me grab a piece of paper and some scissors. Mr. Canfield, are you unprepared for class? Shut up. Oops, excuse me, pardon me. That was, I don't know, I burped. That was. That's scissors enough. Okay, so it's a 16 by 30 piece of metal. Pretend this is my 16 by 30 piece of metal. So like this would be my 16 side, this would be my 30 side. And we're gonna make a box out of it. How am I gonna make a box out of this? Well, it says, by cutting squares of equal sides from the corners. Okay, well, let's try that. Let me cut a square out of the corner. So I'm gonna cut, just pretend with me that that's a perfect square, okay? I'm just gonna tear. So I cut a little square out of that corner. Now I gotta cut the same square out of each corner. So, and again, if we were doing this for real, we would measure it. We wouldn't be using paper, we'd be using metal. And we wouldn't be tearing it, we'd be cutting it with some sort of thing that cuts metal. Eyeball this because it's only so important. Okay, so there, I cut a square out of each corner. Now I've got, how the heck is this gonna be a box? Check it out. So, I guess I need to fold just a little bit more on each side there. It's a box. Ooh, look at the box. It's a beautiful box. Oh, I mean, ooh, it's a box. I made a box. So notice it does not have a roof because it's an open box. All right, let's talk about the dimensions of this box. This side is no longer 30. Because I chopped in there and I chopped in there, right? It used to be 30, but now I chopped in a little bit. So what I'm gonna say is, it's 30. How long is this side? I don't know, I'm gonna call it X. I'm gonna call this side X. So I took 30 and I chopped in X and then I chopped in another X. Or you could just say 30 minus 2X. How about this 16? Well, I took 16 and I chopped in X and I chopped in X because it said that we chopped in squares. So when I'm looking at this equation that I'm dealing with here, the way that I'll often draw this, that's a bad rectangle. I'll do this sort of thing. This is completely unique. Nobody else does this. No, everyone does this. So this was 30 and then minus 2x. This was 16 minus 2x. Because this is x, this is x. Way more labeling than you need to do. Just having some fun with it. Okay. So I could call the length of my box 30 minus 2x. I could call the width of my box 16 minus 2x. I could call the height of my, what's the height? That's the height. X. Got my volume equation in one variable. All right, so before I go and, actually, I am curious. I'm gonna do this two ways. I'm gonna take the derivative like this, and then I'm gonna FOIL it out and take the derivative and see which one is easier. So you do your way, but if you're curious, stick with me. So I can do product rule with this, And product rule says take the derivative of the first one, leave everything else alone. Then take the derivative of the second one, leave everything else alone. Then take the derivative of the third one and leave everything else alone. Yeah, product rule just, it works down the line. So, looks like I get a negative 2x, so negative 32x plus 4x squared. Then I get negative 60x plus 4x squared. Then I gotta FOIL this out. 30 times 16, I don't know that. Well, 3 times 16 is 48, right? So that'd be 480. So 480 minus 60x minus 32x plus 4x squared. So I got 12x squared minus 60 minus 32 minus 60 minus 32. Well, that's what? 60, it's 92, so 184 plus 480. So that's V prime. So it looks like I might have taken the longer route, because if you're just going to take this and FOIL it out first, I still had to FOIL this part out, and then I just distribute an x. So like that, V is just 480x minus 92x squared plus 4x cubed. So then V prime is going to be 480 minus 184x plus 12x squared. That was a little bit easier. It doesn't matter though. Okay. So I'm setting it equal to 0 and solving it. It's a polynomial. I know it's never undefined. I know the two ends are divisible by 12. I'm not sure if 184 is divisible by 12. So I am gonna just do my usual way that I figure stuff out like this, and just divide everything by 2 first. It's tedious this way, but it's what my brain prefers. I can divide everything by 2 again. That's what, 46, and then 120. I can divide everything by, oh no, can't divide everything by 2 anymore. Can't divide everything by 3 either, because 46 is not divisible by 3. Okay, so it looks like we're stuck there. Okay, so now you can either factor this, or quadratic formula it. It doesn't matter, but there's going to be 2 different x values that work for this. So, yeah, you do you. If you're going to do quadratic formula, though, 46 squared is going to be kind of a nightmare. So I'll walk through my factoring process. And again, just, skip ahead if you know what you're doing. So I know I'm going to have 3x and x. How do I know that? Well, I need to, when I FOIL out, the first term is going to be 3x squared. So the only way to get 3x squared is by having a 3x and an x. If this was another number like 8, well, then we'd have options like 2 and 4, 8 and 1, and we'd have to kind of play around with it. Then I'm going to look at my 120. I'm multiplying to a positive 120, but I'm adding up to a negative 46. So that tells me I'm going to need double negatives in here. So to multiply to 120, I also have to add to a negative 46. So I'm thinking 20 and 3 Yep, good job, because 20 times 3 is 60. That's not even right. So I'm thinking 20, nope, 40 and 3. That's what I meant to say. I'm thinking 40 and 3. No, that's still not it though. So I was thinking 40 and 3 because of the 46. I was thinking I could put like the 40 here and the 3 here. But 3 times 3 is 9, so that's not going to work. Let's see. You know, I'll show you. Here's, okay, 1 and 120. Does that work? Think about the options. No. 2 and 60. Does that work? Let's see, 60 minus 6. Nope. 3 and 20. Does that work? I think I just checked that one. So what I'm doing is process of elimination, starting with 1, I just go down the line. If you don't do this, it's easy to go back, and it's like I'm circling back to 3 and 20 again, even though I thought about it earlier, because I was too hasty. Yeah, 3 and 20 is not even right. 3 and 40. So no. What about 4 and 30? Let's see. 4 times 3 is 12, so no. 5 and 24. So that's 15. No. 6 and 20. Well, that's going to be 18, so that's 38. So no. 7, I don't think goes in. 8 and I don't even know what that is. 120 divided by 8. That's going to be 1, 8, 4, 15. So that's going to be 24 plus 5. No, okay. Notice this can take a very long time. 9, I can't see how 9 goes into 120. I don't think it does. Yeah, because it's going to be 30 and 30. Yeah, okay. And then 10 and 12. Let's see. So there we go. Because if I make 12 times 3, that's 36. 10. So 3 times 12 is 36. There's 10, that's 46. All right, so my two x values are x is equal to 12 and x is equal to, what, 10/3? All right, cool. Go back to your box real quick. One of those is impossible. 16 minus 2x. If x is 12, 16 minus 24, this side length is negative. So x is equal to 12 is impossible. X is equal to 10/3 is my only possibility here. So what size square should be cut out to create a box? A square with sides of 10/3. And then it says, what's the max volume? Well, volume is equal to 30 minus 2 times 10/3. 16 minus 2 times 10/3 times 10/3. All right. I'm going to say 10/3. I'm going to store that as x, just to save myself some writing. So 30 minus 2x. 16 minus 2x. X. 725.926. And inches cubed, because that's volume. All right. Well, I'm going to break here and continue on with question 5 next.